Evaluate the following integral and then find the derivative of your answer with respect to x. What do you notice? Okay, so let's do this. What is the antiderivative of 2t?
T squared.
What is it? T squared. Very good. Not 1/2 t squared. Remember, you add 1 and then multiply reciprocal. If you multiply the reciprocal of 2, it's 1/2, and 1/2 times 2, you get the 1 right there. So then you have x as the upper limit and 4 as the lower limit. Then we use the fundamental theorem of calculus, right? So we're now going to do the upper limit minus the lower limit, right? So it's going to be x squared minus 4 squared. So this is x squared minus 16. Does everybody agree that's what I would get? Okay, so now we're going to find the derivative of x squared minus 16. So what is the derivative of x squared minus 16? 2x. It's not supposed to be hard. Yeah. So what do you notice? What do you notice if you compare the 2x to the integral we started with? I'm sorry?
Yeah, 2x, 2t.
Okay, yes. So, but do you see that this upper limit, if I were to just put the x in where that t is, I would actually get this answer directly? Do you see that?
What the derivative of the integral is.
Antiderivative and then derivative. Would be that's like what you did.
So essentially yeah, I'm going back to the original. However, there's an x here, not a t anymore, right? So do you see that if a shortcut would be just to put the x directly in there, and I could go directly from there to this step. Yes? Okay, so this is the fundamental theorem of calculus part. Now, in this book it's part 1, in other books it's part 2, so I wouldn't be concerned about what part it is. It's just another branch of the fundamental theorem of calculus. And it basically specifies the relationship between two central operations of calculus, which is so differentiation and integration. You could say anti-differentiation, but we usually say integration, right? Okay, the first part of the theorem, sometimes called the first fundamental theorem of calculus, shows that an indefinite indefinite integration can be reversed by differentiation. The first part is also important because it guarantees the existence of anti-differentiation for continuous functions. So on your recipe card, you should actually write this theorem out. So the fundamental theorem of calculus part 1 specifies that if f is continuous on closed interval ab, then the function g defined by g of x is equal to the integral from a to x of f of t dt, where a is less than or equal to x is less than or equal to b, is continuous on closed interval AB and differentiable on AB, and g prime of x equals f of x. So basically what they're saying here is if I find the derivative of this, it's essentially putting this x into there and getting f of x, just like what I kind of showed up there. Okay, so an alternate notation is g prime of x is equal to d dx of the integral from a to x of f of t dt, which equals f of x. All in one kind of statement there. So if you think about this for a second, if we have a graph of some function here, and here's a, and here is b, and here is, say, x, right? Does everybody see that essentially if I wanted to find the integral from a to some x, wherever that may be, that essentially what I'm doing is that is equal to whatever that f of x is. Essentially, you'll see this a lot when, and they'll put numbers in here, so that's basically the accumulation of area going on there. It's a pretty easy concept once you get it, but it's funny how many people, once they stop using this and get ready for the exam, they forget all about this, that it's just a simple, you know, kind of plug and go, right? Anyways, in other words, the derivative of the antiderivative function is the function itself, evaluate at the x value or upper limit of the integral. So not all the time x is the upper limit. So we got to use our properties to end up doing that. So what's this equal to? I'm sorry? X squared. By the way, this doesn't always have to be a 1. It can be a 1,000. It's what's called a dummy number. Like it's not supposed to be mean. It can be anything.
Could it be another
It cannot be another x or variable or function. No, it has to be a number. It has to be like any constant of some sort. Okay, what about this one? What would this be? So we're finding the derivative of the integral, right? So that just means this goes in, and so what do we get? What happened to the sign, though? So it would be sine of x squared plus 2. Done, right? It's just going right where the, yeah, you get it? Okay.
-3 sin x.
So we cannot use the fundamental theorem of calculus unless A, it's continuous, which we've all just kind of blindly plugged it in, and we didn't actually discuss that part of it. It has to be continuous. And the other thing is the variable has to be on the upper bound. So we know how to treat this. What do? Yeah, we put it as a negative. So we're actually finding the negative derivative of 5 to x of 3 sine t. I already put the t there. dt. So what do we get then? -3 sine x. All right. So if capital H of x equals some constant to some function this time, do you see this is a function, not just a variable, then the derivative can be found by using the chain rule. So since h of x is the remember we kind of use the notation for antiderivative of f of x to be capital F of x. So this is going into that. Then the derivative is going, it's going to be, do you remember what we did with the chain rule? What did we do? So it's the derivative of this with the outside left alone. So it's going to be f prime of u of x times the derivative of the inside, which would be u prime of x. Yes? So, again, make sure that this is just some arbitrary number at the bottom. Good to go. Yeah. This is continuous, so we can go in and we get e to the power 10x, but then we have to, because this is a function and not just a variable, we have to multiply it by the derivative of that function, which is secant squared x. Very good. So if you want, you can put brackets around both of them. Yeah. All right. Keep on going. What about this one? What about this one? Okay, so this is a constant, this is a function. So the function's going to go in there. So we get 1 over 1 plus sine squared x times the derivative of the top, of this upper limit, which is cos x. So this might be simplified to be cos x over 1 plus sine squared x.
No, isn't the square.
No, we don't have to find the derivative of t squared here.
Okay.
Yeah, no, that goes directly in. It's all good. Yep. Okay, this one's a little bit of a different situation because we have a function on the lower limit and a function on the upper limit. So we got to use our integral properties, split it up, right? So this is equal to d dx of, how can I split this up? Because you have to have, in order to use the fundamental theorem, this has to be an actual number, a dummy number, right? You can't just ignore a function. So I'm going to do this in multiple steps, and you'll see that you can skip steps along the way if you want. Because at this point, because x squared shouldn't be on the bottom, you probably already flip it. But I'm going to do it one step at a time here. So I'm going to do it as the integral from x squared to, who cares a number? Just pick a number. I heard 4. I like 4. I like 4. Okay, so then I'm going to have cos t dt plus, now what's this next interval going to be? If I chose a 4 there, how do I put them together? This has to be a 4 here, and the upper limit is going to be x cubed, cos t dt. Does everybody understand that this, with the Carson math, right? Do you guys remember what I meant by that? Okay, that this would go to that. I haven't changed anything. However, this cannot be on the bottom. So, like I said, I'm showing every step. So equals d dx of, we're going to flip the integral. So it's going to now be minus, 4 is going to be on the bottom, x squared going to be on the top, cos t dt plus 4 is on the bottom here, x cubed on the bottom top, cos t dt. Everybody good with what I did? So now I'm going to find the derivative. So the derivative is, using the fundamental theorem of calculus, this goes in, right? So we get negative cos of x squared, but then we have to do the chain rule. So times 2x plus fundamental theorem calculus, the x cubed goes in. We get cos of x cubed, and then we have to do the chain rule of x cubed. That would be 3x squared. Everybody good? Okay, let's move on. Oh, do you want to try this one? You guys can try. You think you can handle it now? Yeah? Oh yeah. Let's try it. Try the rest. So this would be sine of the square root of x to the power 4 minus 1 plus 1 times, we have to find the derivative of this, so that would be 4x cubed. So then this would be sine of the square root of x to the power 4, right? Times 4x cubed, and we can square root that, and we get, as a final answer, 4x cubed sine of x squared. Is that what you guys got? Okay. So this one, we have to split it up, right? And you don't have to do every step, because at some point you're going to have to start skipping steps because you're going to run out of time on the exam, right?
Pick a random number.
Random.
Yes.
Huh? Like what?
Pick random.
Like 2, yeah.
Alright.
Most people pick 1 for some reason. You'll see a lot of the questions are 1.
Why not 0? Whether to be on
You like 4? Okay.
Who's your favorite?
I'll use 4 just because Rachel likes 4. Okay, so I skipped the step where I wrote it as sine x to 4. I just went directly to switching it to the, you know, reverse the integral and put the negative there. Yeah? Okay, I didn't lose anybody there? So then this would be negative sine cubed x minus, or so that would be a plus the square root of sine x. This whole thing is multiplied by the derivative of sine x, which would be cos x, plus, then x goes in there, and I get x cubed minus the square root of x.
Oh, it's x over side.
So, did you get that? Just so you know, if this is a multiple choice, they may have this multiplied in to simplify, because usually brackets aren't the, you know, yeah. Okay, so for the last one, just to refresh our memory, we're going to actually do part 1 and part 2 together. Part 2 is where you find the antiderivative first, and then you do the subtraction, and then you find the derivative. So we're going to do both just to prove that we get the same answer. Okay, so we're going to do part 2 first. It's part 2 in the textbook, but it, like I said. Okay, so part 2 says you find the antiderivative. So the antiderivative of t squared is 1 over 3t cubed, yes? From 1 to x. Does everybody know what I'm doing here? So now we're going to plug her in. So we get 1/3 x cubed minus 1/3 times 1 cubed. Are we good so far? So we get 1/3 x cubed minus 1/3. And then we're supposed to find the derivative of this, right? So then d dx of 1/3 x cubed minus 1/3, what do we get? We get x squared. And so now we're going to do FTC part 1. Of course, that's the easy one, right? D dx of the integral from 1 to x of t squared dt. You just plug that back in and you get x squared. And so do you see you get the same thing? I've had some students in the past where they forget this easy thing and they do this whole thing to get that. It wastes time. So if you can just know how to do this, is way better, right? You won't get the wrong answer, it just wastes time, right? So I think I heard somebody say, what happened to the c? That's only when I'm doing indefinite integrals that I have a plus c, right?
Yeah.
Meaning, if I have the integral of, I don't know, t squared dt, that's an indefinite integral. That's where I'd have the plus c. The only reason why we don't have a plus c when we have the integral from, I don't know, say 0 to 1 of t squared dt is because when we find the antiderivative of this and then we do the subtraction, the c's cancel, right? And I showed you that in that video there. So